Scientists are studying the growth of two different populations. First of all, we're looking at the first population, modeled by this equation. A and K are positive constants, T is the time in hours from the start of the study. And there were 1,000 bacteria in this population at the start of the study. Well, actually, that's going to be when T is 0, which means the exponential term will just become 1. That is our value of A. And it took exactly 5 hours from the start of the study for the population to double. So it's going to be 2,000 then. So 2,000 is going to equal our 1,000 times e to the 5k, because I've substituted in t as 5. That means e to the 5k is going to equal 2, and therefore 5k is going to equal ln 2. So k is a fifth ln 2. That's its exact value. Remember, this is a model, so we'll give our answer to three significant figures, 0.313862. And then I'll round it. So n equals 1,000 times e to the 0.139 t. Hence, find the rate of increase in the number of bacteria in this population exactly 8 hours from the start of the study. Give our answer to two significant figures. Got enough space up here to do that. So that's going to be dn by dt, the gradient function, and then I'll be substituting in t equals 8. So for this sort of exponential, the thousand just kind of stays there. We just have that as a constant. And then e to the kt differentiates to k e to the kt. So I'm going to be timesing by 0.139. So I'm just going to write it down exactly to start with. So 138.629 multiplied by e to the 0.13862. Okay, so I've left it exact rather than using the rounded version. I always think that is good practice in science to do that, regardless of whether the mark scheme lets you get away with not doing that. So when t equals 8, dn by dt, just need to substitute that in. Oh, I forgot to put a t there, sorry. So it's going to be this times e to 0.13862 times 8. 420.214. So to two significant figures, 420. Number of bacteria in the second population is modeled by this equation. K has the same value as that found in part A, and T is the time in hours from the start of the study. Given that T hours after the study, the number of bacteria in the two populations was the same, find the value of T. So we're going to have slightly different, okay, so this one's going to start at 500, but maybe it goes up more quickly. And then the other one starting at 1,000, okay, maybe a bit less quickly. So we're looking at this point here where they are the same. And that's going to mean that 1,000 e to the 0.13862 t, although I can now use capital T to be fair, is going to equal 500 e to the 1.4 times 0.13862 t. This is our equation to solve. I'm going to divide through by 500 and divide through by this exponential. So 2 is going to equal e to the 1.4. I'm going to leave it like this for the moment. It's 0.13862t divided by But remember, these are powers. This is like x to the a over x to the b, so we can just subtract them, which is 1.4 lots of this minus 1 lot of this, which is going to give me 0.4 lots of this. If you prefer, you can work that out and then minus that on your calculator, but it is just going to be this. That means 0.4 times 0.13862t is going to equal ln 2. I've just undone the logs. You can apply ln to both sides if you prefer, but that is what this is going to give. And then t will be ln 2 divided by that. Which gives 12.500. Rounded to three significant figures, 12.5 hours, but yeah, that's the main thing.